This problem focuses on deciding how much quay length to build and how to segment that length into berths. It is an infrastructure design decision, but it also affects day-to-day berth allocation, because vessels arrive over time with uncertain schedules. The core trade-off is straightforward. More infrastructure reduces congestion and waiting, but it requires large capital investment. The challenge is that arrivals, vessel sizes, and service times are uncertain, so a design that looks good on average can perform poorly in adverse scenarios. Mediterranean Logistics Hub is planning an expansion and must choose the total quay length and the number of berths. Operational data indicates an average of 45 vessels per week and arrivals that follow a Poisson process. Vessel lengths range from 180 meters for small feeder ships up to 400 meters for ultra-large vessels. Average berthing time is 18 hours, but it varies by vessel size and cargo volume. These uncertainties directly drive waiting and utilization outcomes. The investment and operating costs make the decision high stakes. Construction is estimated at $2.5 million per 100 meters of quay length. Waiting is also expensive at about $8,000 per hour of vessel delay when you account for port fees, fuel, and schedule disruption. Too few long berths waste capacity when small ships occupy oversized berths, while too many short berths cannot handle the largest ships. We will use a tiered approach. Tier 1 is a robust optimization model that protects against worst-case scenarios inside an uncertainty set. Tier 2 uses a divide-and-conquer decomposition to scale the problem. Tier 3 applies a Firefly algorithm metaheuristic to handle complex multimodal solution landscapes. Tier 5 introduces an integrated digital twin. Tier 7 focuses on human and artificial intelligence collaboration through a Centaur model. In Tier 1, the decision variables include the total quay length and which berth segments to build, as well as their individual lengths. The model also tracks expected waiting time under each scenario. The objective minimizes construction cost plus the worst-case waiting cost over an uncertainty set. This means the design is evaluated not only on average performance, but on how it behaves in high-stress conditions. The model includes a set of scenarios representing different arrival and service patterns. It also includes a set of vessel types, which capture different length requirements and service characteristics. Finally, it includes a set of berth segments. These segments represent the building blocks used to construct the full quay length and define how the quay is partitioned into individual berths. Key parameters include scenario-dependent arrival rates and vessel type length requirements. The model also uses vessel type probabilities within each scenario and service rates. On the economic side, it includes the cost per unit length of quay construction and the cost per unit time of vessel waiting. It also includes an uncertainty budget parameter that controls how conservative the robust design must be. The total quay length is a primary decision variable. A binary construction variable indicates whether a specific berth segment is built. Each segment has a length variable and each scenario has an expected waiting time variable. Together, these allow the model to translate infrastructure choices into congestion and delay outcomes under each scenario. The objective is the sum of construction cost and worst-case waiting cost. Construction cost scales with total quay length, while waiting cost is multiplied by the waiting cost rate. The robust part is the maximum over the uncertainty set. Operationally, this discourages designs that are fragile, meaning they look cheap, but create severe congestion in certain plausible traffic conditions. The uncertainty set defines which scenarios are considered in the worst-case evaluation. It is controlled by the uncertainty budget parameter. Conceptually, the uncertainty set limits how far scenario arrival rates can deviate from nominal values. A larger budget means the optimizer must protect against a wider range of adverse conditions. This constraint links the total quay length to the sum of the constructed berth segment lengths. If a segment is not built, its binary variable is 0 and it contributes nothing. This enforces accounting consistency. Total quay length is exactly what is built through the set of segments. Each berth segment must satisfy minimum and maximum length rules when it is constructed. This prevents unrealistic segments that are too short to berth meaningful vessels or too long to be practical. Operationally, these bounds help ensure the berth configuration can serve the vessel mix and supports a manageable allocation policy. This constraint provides an approximation for expected waiting time using a queuing formula for an M over G over C system. It links waiting time to utilization and an effective service rate. The practical meaning is that as utilization approaches 1, waiting time increases sharply. This is the congestion cliff that robust design aims to avoid. Utilization is defined as demand divided by effective service capacity. In each scenario, demand depends on scenario-specific arrival rates and vessel type probabilities. Capacity depends on how many berths are built and the effective service rate. This variable is central because it drives both waiting and feasibility. This framework figure summarizes how robust optimization connects infrastructure decisions to waiting and cost outcomes. It shows the flow from uncertain arrivals and vessel types to utilization, and from utilization to waiting time. The key takeaway is that the design must be feasible and cost-effective across a family of scenarios, not just under a single forecast. The example uses 2 vessel types. Small vessels require 200 meters of berth length and have an arrival rate between 8 and 12 per week. Large vessels require 350 meters and have an arrival rate between 3 and 7 per week. Service rates are 4 vessels per week for small and 2 vessels per week for large, and the uncertainty budget is set to 1. The reported robust solution builds a total quay length of 950 meters. It uses 2 berths of 300 meters and 350 meters. The reported worst-case expected waiting time is 4.2 hours, and the reported total cost, including construction and expected waiting costs, is $27.6 million. Tier 2 decomposes the integrated problem into 3 subproblems: capacity sizing, berth segmentation, and allocation verification. This decomposition reflects different decision timescales. Capacity sizing is driven by long-term forecasts, while segmentation is driven by vessel size distribution and flexibility needs. Verification ensures the allocation is feasible. This figure shows the hierarchical structure of the decomposition and how the outputs of one stage become inputs to the next stage. It highlights why this approach is scalable. Instead of solving everything in one complex model, you solve smaller problems sequentially and iterate if needed. This pseudocode initializes a solver with vessel arrival rates, vessel lengths, service rates, and cost parameters. It defines a capacity sizing step that computes required capacity based on demand and a target utilization factor, then converts that capacity into a total quay length using a weighted average vessel length and a buffer. This section performs berth segmentation. It uses weighted mean vessel length and then greedily assigns berth sizes, starting from the largest feasible size. The goal is to create berths that can accommodate the vessel mix while controlling wasted space. This section verifies allocation feasibility. It builds a feasibility matrix indicating which vessel types fit which berth sizes. It also computes utilization metrics per berth based on compatible vessel demand. This is essential to understand where congestion risk may concentrate. This section computes costs. It estimates construction cost from total length and uses a queuing approximation to estimate operational waiting cost. It then annualizes construction cost using an amortization assumption and combines it with operational cost to produce a total annual cost metric. This final portion returns the integrated design metrics: total quay length, berth sizes, construction cost, annual operational cost, total annual cost, and average utilization. Operationally, this output supports a practical decision workflow because it provides a complete design proposal plus a cost and congestion summary. The reported run produces a total quay length requirement of 1,247 meters. The reported berth configuration is 440 meters, 440 meters, and 367 meters. Reported construction cost is $31,175,000. Annual operational cost is $628,400, and average utilization is 82.3%. Tier 3 introduces the Firefly algorithm. Each Firefly represents a candidate berth configuration, and brightness corresponds to solution quality, meaning lower total cost. Fireflies move toward brighter neighbors with a distance-dependent attractiveness and a random movement component. This combination promotes convergence while preserving exploration. This figure illustrates the search behavior of the Firefly algorithm and how candidate configurations evolve over time. The key idea is that the algorithm can navigate multimodal landscapes where there are multiple local optima and where different berth segmentations can yield similar costs. This pseudocode initializes a population of fireflies as random berth configurations that respect constraints like minimum berth length and maximum total key length. It evaluates each configuration by combining construction costs with waiting cost penalties based on assignment feasibility and utilization. This section defines how distance between two configurations is computed, typically by comparing padded berth length vectors. It also defines the movement rule where a less bright firefly moves toward a brighter one with a strength that decays with distance, plus a random perturbation. This section describes the main optimization loop: evaluate fitness, update brightness, move fireflies toward better solutions, and record progress over iterations. The algorithm periodically logs best and average values to monitor convergence and detect stagnation. The reported progress starts with an initial best fitness of $42,150,000. It improves to $38,920,000 by iteration 20, reaches $32,750,000 by iteration 80, and reaches $29,580,000 by iteration 140. The reported best total cost is $29,580,000. The reported berth configuration has 4 berths with lengths 325, 425, 380, and 285 meters for a total key length of 1,415 meters. The reported improvement over the initial solution is about 30%. Tier 5 expands the problem into a system of systems digital twin that integrates berth infrastructure with vessel traffic, cargo handling equipment, yard operations, and hinterland connections. The digital twin enables real-time optimization, predictive analytics, and dynamic adaptation of berth infrastructure to changing operational conditions. This architecture includes 5 layers: physical assets with sensors, operational data feeds, analytics models, simulation models, and a decision support layer. The key value is that it captures interdependencies, such as how berth allocation affects crane positioning, yard congestion, and landside flow. In the example, Mediterranean Logistics Hub manages 3.2 kilometers of key length across 8 berths and processes over 50,000 data points per minute. It uses 240 structural health sensors, 15 weather stations, 32 water level monitors, and 18 radar units. It integrates with 12 port management systems and maintains connectivity with 6 major shipping lines. The reported machine learning accuracy is 94% for 48-hour vessel arrival prediction and 87% for 7-day cargo forecasting. The system processes berth allocation decisions in under 45 seconds while considering 15 constraint categories and optimizing across 8 performance metrics. Reported outcomes include berth utilization increasing by 23%, vessel waiting times decreasing by 41%, and infrastructure return on investment improving by 18%. Port planners can evaluate infrastructure modifications quickly. The reported analysis evaluates 120 berth extension alternatives. The best option is extending berth 6 by 85 meters, with a reported net present value of $12.4 million over 15 years. Tier 7 focuses on collaboration. Humans contribute strategy, stakeholder management, creativity, qualitative risk assessment, and ethical considerations. Artificial intelligence contributes large-scale optimization, pattern recognition, scenario analysis, real-time processing, and bias reduction. Explainable artificial intelligence is essential for trust and transparency. This figure summarizes how human and AI capabilities are layered and connected through decision support interfaces. It emphasizes explainability components like feature importance, sensitivity analysis, counterfactual explanations, confidence intervals, and interpretable decision paths. The Port of Rotterdam example involves a €3.2 billion investment across 20 new berths spanning 4.2 kilometers of quay. The AI system processes 15 objectives, integrates 150 data sources, uses models trained on 25 years of data, and runs stochastic simulation at a rate of more than 10,000 scenarios per hour. The human and AI team evaluates 2,847 configuration alternatives over 18 months. The AI initially recommends 6 berths of more than 400 meters each, optimized for throughput. Human experts identify missing priorities such as environmental constraints, future fleet evolution, operational flexibility, and political feasibility. The final solution uses 8 berths ranging from 285 to 450 meters and achieves 97% of the AI optimal throughput, 15% better environmental compliance, and 23% higher flexibility. The reported recommendation acceptance rate is 87%, and the reported human override accuracy is 92%. Reported collaborative solution quality is 31% better than pure human decisions and 18% better than pure AI solutions. Reported average decision confidence is 8.4 out of 10. These practice questions test your ability to build complete models and analyze algorithmic behavior. Tier 1 questions focus on robust optimization and multi-berth segmentation under uncertainty. Tier 2 questions focus on decomposition, greedy construction, and local search. Tier 3 questions focus on parameter tuning for Firefly and designing genetic and hybrid metaheuristics. Tier 5 and Tier 7 questions focus on digital twin architecture and explainable human and AI collaboration. Berth and quay length design is a core port infrastructure decision that must balance capital cost with congestion and waiting costs over many years. Robust optimization protects against uncertainty, decomposition improves scalability, and metaheuristics explore complex design landscapes. Digital twins enable continuous data-driven optimization, and human and AI partnership improves decision quality and stakeholder acceptance.